Let me see the number because the other professors asked me how many students are present. So 25. Okay. No, let me go to the file. So random sampling. So now the thing starts to be very important because now we start with random sampling. So we studied descriptive statistics, probability theory, and now we're going to look at random sampling. Random sampling will be a very important lecture because it will provide an instrument for us to introduce, not today, so for sure tomorrow, the so-called inferential statistic, which is the most important field of statistics. So here I start by reading with you, and then I comment if necessary. We represent the population with a random variable x, and we are interested in studying the main characteristics of the population, parameters, moments, usually unknown. Remember that in the first lecture, I introduced you 5 very important concepts of statistics, and I told you, guys, we will discuss later about this concept. And now it's the moment. We discussed, remember, the population, the concept of sample, the concept of variable, the concept of parameter, and the concept of statistic. And I told you that the population is the total set, is the total set of subject of interest in a given study. And I denoted with X the variable of interest. Typically, guys, in statistics, we simply say that we represent a population with a random variable X. That is, we represent the random variable describing the characteristic of the population of interest, for example, the income, through the random variable X. So if you measure, typically in a statistical study, if you want to study the income of all the Italians, you introduce a random variable X, which describes the income for each Italians. So it is a random variable that assumes a different number according to the specific Italian you consider. So, and typically, to simplify, we say that we represent the population through the variable X. So we say that we represent the population through the variable X. To be precise, this means that we represent the variable of interest, for example, the income of all the Italians, so one by one, through a random variable X. But to simplify, in statistics, we say we represent the population through a random variable X. And we are interested in studying the main characteristic of the population. As I told you in the first lecture, parameters are constant characterizing the population. So are characteristics of the population typically unknown. And I told you we represent the population through a random variable. And you know that a random variable has its own distribution, has its moments, and the moments of a random variable are constants. Okay? So suppose, for example, let me read. X, capital X, could, for example, be the random variable describing the duration of a particular type of tire. Okay, if you select a given tire, you have a particular duration, but X is a random variable that can assume different values, and the different values that X can assume are the values that all the tires can, all the duration of the different tires can assume, because if you select a tire, a particular tire has a duration, another particular tire has another duration. Okay, or it could be also the income of the Italians, because it's a random variable, because the value assumed by X depends on the particular Italian you select. Okay, an Italian, a particular Italian has an income, another Italian citizen has another income. So X could be the random variable, for example, describing the duration of a particular type of tire. So we say that the population of the tire follows, we denote, for example, the population of the tire of a given brand by X, or the age of all the Italians is described by the random variable X. The income of all the citizens of Milan is described by a given random variable X. So X could be the random variable describing the duration of a particular type of tire, the age of the Italians, the income, etc., depending on the study of interest. But in general, very simply, statistics, we say that the population follows a given distribution described by the random variable X. So X is a random variable describing the population, okay? Okay. Suppose, for example, guys, that X, which is the random variable describing the population, follows, for example, it's only an example, guys, to understand the problem, follows a normal distribution with mean mu and variance sigma square, with mu and sigma square unknown. And we want to get information about mu and sigma square. For example, if X is the random variable describing the duration of Pirelli tire of a given type of car, or I mean, of a particular type of a particular, I repeat, suppose that X is the random variable describing the duration of Pirelli tires of a particular type, okay? And you are interested in studying which is, guys, the true average, the expected duration of a Pirelli tire. If you buy a Pirelli 4 Pirelli tires for your car, which is the expected duration of these tires? Okay, which is the expected duration? Okay, the expected duration is unknown, typically is unknown, which is mu, is the expected duration. That is, suppose you can select, you can measure the duration of all Pirelli tires, then mu is known, but obviously this is unfeasible, because to measure the exact duration of all Pirelli tires, you should consume all Pirelli tires. You should be able to see their duration until the end. Then you make the sum, then you divide by the number and their number, and you get mu. But this is obviously unfeasible, because Pirelli tires are continuously new tires are produced. Okay, and so which is the expected duration of a Pirelli tire is mu, but it's unknown. Okay, is unknown. You can try to get information about mu, but the expected duration is unknown. Is mu, is a constant which is unknown, which is the variance of the duration of Pirelli tire. This is also unknown, guys, because in principle, to compute exactly sigma square, you should consider all Pirelli tires. You should measure again the duration of all the Pirelli tires, but this is unfeasible, impossible, because you should look at all Pirelli tires. Okay, so you don't sell them, you consume it only for your pleasure, and then you have to measure what you can compute the variance, but this is obviously stupid and unfeasible in practice. So, or suppose, for example, that you want to measure the income of all the Italian. Mu is the average income in the population, is the average income of all the Italians. Sigma square is the variance of the income of all the Italians. So, guys, unless you consider all the Italians living in this moment, and you make the computation of the variance that we studied with me, you are not able to get mu and sigma square. Okay, and as I explained a lot of time, in the great majority of experiments, you cannot work using the complete population, but you have to select a sample. So since you select a sample, you can't get a perfect knowledge of mu and a perfect knowledge of sigma square. So for this reason, in statistical study, typically we want to get information about the unknown parameters characterizing the distribution of the population. the population can be represented through a random variable. So, and in other terms, what you want to get is information about the moments of a random variable, because remember, mu is a parameter of the population and is also the raw moment of order 1, is the expectation of the random variable x. Sigma square is the central moment of order 2, okay, and is a characteristic of the population, okay. But unless you study all the population, you cannot get a perfect knowledge of mu and a perfect knowledge of sigma square. Okay, so when you perform a statistical study and x is the random variable describing your population, you are interested in getting information about the unknown parameter characterizing the distribution of the population. But due to cost and to technical problems, due to the fact that sometimes it's not even possible to define very precisely the population, for example, consider the tires of Pirelli, which is the population. Oh, the population continuously change because continuously new tires are produced, okay, and sold. So what can you do, guys? So for this reason, you have to use the information provided by one or more sample, okay? And you have to use in a consistent way, in a theoretically founded way, the information provided by the sample to try to get information about the population. So we read, in theory, to get a perfect knowledge of mu and sigma square, we should examine all the population, all the elements of the population. In most cases, this is not possible for different reasons, times, costs, and sometimes it's not even possible to define the population completely. Okay, so to study the unknown parameters of the population described by the random variable x, we need thus to select one or more samples. And here I provided the definition of random sample. A random sample, it is a sample such that every element, then I will explain, of the population has a known and not zero probability to be selected from the population and become an element of the sample. If x is a random variable describing the population, and we want to select a random sample of dimension n, we denote a random sample as a vector in this way. Write capital X1, capital X2, etc., etc., capital Xn. So we use this notation with capital letter to denote the random sample. And on the contrary, as we did already in the first lecture, we denote instead the selected sample, that is the observed one, by using small letters. So this denote the notation used to denote a random sample. With small letters, you denote the observed sample, that is the selected sample. Let me read below and to explain and read that. You see that outline everything with the red. So this definition is very important. So a random sample, which is denoted in this way, remember capital letters, this is a random sample of dimension n, is a random vector made up by n independent and identically distributed random variables to the population. That is, xi for I that goes from 1 to n follows the same distribution of the population x. And now I explain. So a random sample, guys, is a vector of n random variables. These random variables x1, x2, xn are independent. And the distribution of x1, the distribution of x2, the distribution of xn is the same of the is the same distribution of the population. And guys, pay attention. Here you have a distinction between these. Do not confuse this sample, which is a random sample, with the observed sample. This is the sample before having selected it. So you want to establish that you study, in order to study the known characteristic of the population, you establish to select a sample. So before selecting a sample, your sample is a random vector. You know that you want to select a sample, for example, of dimension 100. You know that you want to select 100 elements from the population, but before selecting it, your sample is a random variable. And now explain why. Because which is the meaning of x1, guys? x1 is the random variable describing the first element of your sample. But before selecting it, guys, before selecting it, x1, which are the possible values that x1 can assume? x1 can assume each of the elements that capital X can assume. Okay, and in particular, the distribution of x1 is the same of x, because I repeat, x1 can assume the same value that x can assume. And if you want to select randomly an element of x1, if you have an element of the population, obviously the probability, for example, to select a particular individual, okay, or suppose we want to measure the income, guys. Suppose I try to do a stupid example. Suppose that x, guys, to simplify, to understand better, suppose that x is the random variable describing the gender of the Italians, okay? Okay, the gender of the Italians. So, and suppose we consider only male and female, okay? Male and female. And suppose that you know that the 70% of the Italians, 70% are females, and the 30% are male. Okay, only to make an example, stupid example. So suppose you want to select a sample from this population, from the variable x. So the first element, so this is a random sample, and the random variable x1 represents what? The gender of the first element of the sample you are going to select. But if you select it randomly from the population, obviously, which are the possible values that the gender can assume? 2, male or female. Which is the possible value that x1 can assume? Male or female. But if you want to select x1 from capital X, obviously, which is the probability that x1 will assume the value male? Guys, is 30%, as in the population. Which is the probability that x1 will be a female? 70%, as in the population. So you see that the distribution of x and x1 is the same. Suppose you select, guys, a girl. So what you get is small x1. Small x1 means girl or female, because this means that you've selected is the observed value. So it's not a random variable anymore because you observed it. Then put this female again inside your population. Okay, keep it here, but then insert again in the population the particular female you selected. Then, which is x2, guys? x2 is the random variable describing the second element you are going to select from the population. But since I introduced again the first selected individual inside the population is unchanged. So again, x2 is a random variable having the same exact distribution of x. So x2 has the same distribution of x. Suppose you select again another individual, and suppose you have a female. So again, female, female. Then put again this individual inside the population. So x3 obviously will have exactly the same the same distribution of x. So it's still a random variable with the same distribution of x. Then select it, and suppose this time you get male. So you have small x3, which is male, etc., etc., etc. So what I just explained you should make you able to understand that before selecting the sample, but simply when you decide to select a sample, this is a random sample which is made up by n random variable. And this random variable, as with this example, showed very clearly, each of these random variable has exactly the same distribution of x. Furthermore, these random variables are also independent. In which sense, guys? Pay attention. I told you, suppose you select the first element of from the population and you get small x1. Then take this individual, put it inside again. Now you see that since we do this sampling, which is based on reintroduction, that is, every element of the population after having been selected, okay, is memorized here, but then you have to put it again inside. You see, each subsequent abstraction from the population does not modify the composition of the population. You see that the distribution of x2 does not depend on the result you got during the first selection. Okay, so the x1, the x2, and the xn are independent. So what you have to remember, essentially, you have to remember at the end of the story, this is the very important property, that a random sample, that is the sample before having selected it, is a vector containing n random variables which are independent. So x1 is independent with respect to all the other random variable, x2 is independent with all the other random variable, etc., etc., and they are all identically distributed to the population. That is, the distribution of x1 is the same of x2, which is the same of xn, which is the same of x. And this is the very important concept. And by using this concept, we will derive in this lecture the distribution of some statistics which are very important in inference. So now let me show. Again, I read again, even if I explain. After having selected the sample, we get a vector of observation. These are numbers. You see the small letters. The observed sample is only one of the possible realization of a random sample. Because, guys, you selected this sample, but this is only one of the possible sample. Okay, because if you select another sample, okay, another sample, for sure, guys, it's very unlikely that you get again the same x1. This time you can get, suppose you get female, male, etc., etc. The second time, if you repeat the sample, if you select another sample in the same fashion, you can get, for example, male, female, okay, etc., etc. So this is only the observed sample. So the observed sample is only one of all the possible realization of a random sample. So a random sample is a vector of random variable. Instead, the selected sample or observed sample is the observed vector, okay, of sample. I mean, is the observed sample. I mean, these are observations, okay. Since a random sample is a vector of random variables, see again that I use the capital letters. A moment, remember, now it should be clear why in the first lecture I used small letters. I used small letters because we were interested only on the observed sample. So it was not a random sample because it was a sample of data. Okay, so since I repeat, a random sample is a vector of random variable, each function of a random sample is a random variable itself, and therefore it will have its distribution. So, for example, if you denote as t, this means, guys, remember we studied together function. T of x1, x2, xn is a function of what? Of n random variables. Okay, suppose you have a function of n random variables, which are the element of the random sample, then a function of a random sample obviously is a random variable itself. The value assumed by the function, this one, depends on the observed sample. After having selected a particular sample, okay, like this one, you can insert into capital X1 the observed value of capital X1, into capital X2 the observed value of capital X2, you get a particular value for your function. Okay, but if you select another sample of small x1, small x2, small xn, put them inside, t will assume another variable, another value. If you select instead another different sample again, you can get another value of t. So t, which is a function of a random variable, random sample, is a random variable itself because its value depends on the selected random sample, so in the observed one. So the distribution, guys, then we will show the example in a moment because I need to introduce them. So here I'm simply talking in general. The distribution of this random variable is called sampling distribution. And now, that being said, guys, we are going to study the sampling distributions that are very useful in statistics and in econometrics. For the moment, I simply tell you this word, but this will be clear later. We are going only to find the exact distribution. Later, we will find the asymptotic distribution, but wait, because for the moment, I don't want to explain the difference between exact and asymptotic distribution. I will do it after having introduced you the sampling distribution, very useful in statistics. And now, guys, we are going in particular to review everything I told you in general in very specific case. Okay, in particular, guys, we are going to find together the exact, but exact will be clarified later, the meaning distribution of the following random variables, which are very important statistics used in statistics, which is the distribution of capital X bar, the distribution of this quantity. Okay, no, don't read, guys, because I discuss one by one. Here I simply anticipate what we are going to see. We want to find the distribution of these random variables, of this random variable, of this one, and the distribution of these random variables. So I need still to explain everything. So don't be scared. So in particular, in order to find the so-called exact distribution, I need to make some assumption. Later, I will relax this assumption to find instead the asymptotic distribution, but I will explain this later. Okay. Now, for the moment, what I explained this morning, I simply provided you the definition of a random sample. Okay, a random sample is a vector, a set of n independent and identical distributed random variable to the population. Okay, and I told you that every function of a random sample is a random variable. This is the concept you have to remember. A random sample is a vector of n independent and identical distributed random variables with the same distribution of the population, and every function of a random sample is a random variable itself, so it will have its own distribution, its own moments. Okay, and I told you. Now I'm going to show you some very important random variables which are used in statistics, and these random variables are called sample statistics, and we will find their distribution. In particular, guys, all these random variable or sample statistics are function of a random sample, and so they will be random variable. In particular, to clarify everything, I start with this one, with X bar, capital X bar. Remember that in the first lecture, we used small x bar. Small x bar, guys, was what? The estimate of the average. We called it arithmetic mean. And given our sample, small x bar was what, guys? Given our observed sample, small x bar was an estimate of x, of mu. We can say that this was an estimate of mu, if you want, of the mean of the population. Okay, small x bar. Okay, but I told you that while mu of the population is constant and unknown, small x bar depends on the sample you select. So capital X bar, guys, is a random variable that's called sample mean. But wait, don't write. Sample mean. So capital X bar, okay, capital X bar, assumption. We made the following assumption. The population, and we want to find, guys, now the distribution of capital X bar. The assumption is the following. The population described by the random variable X follows a normal distribution with mean mu and variance sigma square. Under this assumption, we want to find the so-called sampling distribution of capital X bar. Capital X bar is the sample mean. In particular, now we derive everything, so we repeat all the things we explained generally to see the practical implication. So consider a random sample taken from X bar. So you want to select, from capital X, a random sample. So a random sample, as I told you, is a vector of n independent and identically distributed random variables. So I denoted them with capital letters. So this is our random sample. Now, I told you that pay attention now, every function of a random sample is a random variable. But which kind of function? X bar, guys. X bar is a function. The sample mean, guys, capital X bar is a function of a random sample because capital X bar, which is the sample mean, is the sum of the element of a random sample divided by their number. So X bar, the sample mean, is defined in this way. But what do you have here in the numerator, guys? You have x1, capital X1 plus capital X2 plus capital Xn. So I wrote it here in this way. What do you have here inside parentheses? You have the sum of n random variables. So a sum of n random variables is a random variable itself. So what I've just shown you is that X bar is a random variable. So if you think to what I told you before, I told you that a function of a random sample is a random variable. Here we saw a particular function of a random sample because X bar, capital X bar, is this function of a random sample. You see, because it's the sum of the element of a random sample divided by their number. Okay. So this again is here. Okay. This is our X bar. So it's a random variable because it is a function of a random sample. So since it is a random variable, guys, we want to find its distribution. Guys, again, let me talk about what we said in the first lecture. Remember that in the first lecture, I used small X bar because in the first lecture, we were interested only on the information provided by the observed sample. So in the first lecture, we worked directly with the observed sample, and small X bar was the observed average, was an estimate. However, guys, but before having selected the sample, you can have infinite, a lot of samples, okay, maybe have also infinite, depends on the dimension. You can have a lot of samples, but for each different sample you can select, you will have a possible different value for this random variable. So we denote as small X bar as the observed value of this random variable. But depending on the sample you select, on the one you observe, obviously X bar will assume different possible values. If you select sample A, for example, suppose you select one sample. You select it, compute capital X bar, given your observed sample, and you get a small value. Call it small X1 bar. Suppose you select again another, put again everything inside your sample. So select another sample, compute again the observed value of x bar, which is small x bar 2. Obviously, you will get another value, different or very close. So what I'm saying is that capital X bar is the random variable that will assume different values according to the observed sample, to the sample you are going to select. Okay, but so you see X bar, however, before selecting a sample is a function of a random sample. So depending the value of X bar depends on the value you are going to select of what? For the first observation, for the second, and for the last one. Okay, so it's a random variable. After having selected the sample, you observe small x1, small x2, small xn, put them inside the formula, and you get an estimate. So this is a random variable. An estimate is only a number. As the random sample is a random vector, the observed sample is a vector of numbers, of constants. So, and since I hope we understood that capital X bar, that is the sample mean, is a random variable because it's a function of a random sample, we want to find its distribution under, I told you, this assumption. And now work with me because we repeat everything. So x1, x2, xn are the element of a random sample. Therefore, they are independent and identically distributed to the population. So our population, by assumption, follows a normal distribution with expectation mu and variance sigma square. Therefore, capital Xi, which is the ith element of our random sample, since is identically distributed to the population, will follow again a normal distribution with expectation mu and variance sigma square. And this is true for all the elements of the sample. So from I equal to 1 to n. Again, we want to find, I repeat, the distribution of x bar. We did already an exercise like this in the in the last lecture. X bar, guys, how can you write x bar, for example, as x1 over n plus x2 over n plus xn over n? What is it, guys? We studied it in the last lecture when we studied the normal. X bar, written in this way, what kind of random variable is? Is a linear combination of 1, 2, n random variables. But these random variables, as I told you, are normal. So x bar, the sample mean, is a linear combination of n normally distributed random variables. So since x bar is a linear combination of n normal random variables with coefficient, which are the coefficient, guys, of the linear combination? Here is like having 1 over n times x1 plus 1 over n times x2. So since x bar is a linear combination of n independent, is a linear combination of n normally distributed random variables with coefficient 1n, 1n, 1 over n, 1 over n, 1 over n, then x bar, thanks to the stability property of the normal, the stability property number 2 that we studied in the last lecture, is also normal. So we find out that if the population is normal, then the sample mean is also normal. So you see that the assumption was fundamental. So if x follows a normal distribution, then x bar, since it is a linear combination of normally distributed random variable, is still normal. And you know, guys, that to characterize completely a normal random variable, you need to find also the expectation and the variance. So we find out for a moment one thing, that x bar is normal. But now we want to find which is the expectation of x bar and which is the variance of x bar. We did already similar computation in a different context, but I think the last exercises we did together in the last lecture. In fact, which is the expectation of x bar? Take the expectation of x bar. Put inside x bar is definition, which is this one. Okay, or if you want, write in a more compact form. What is it, guys? This is the sum of the xi, capital Xi, divided by n. 1 over n is a multiplicative constant. So you see, property of expectation. Take the multiplicative constant outside. So you have 1 over n times the expectation of a sum. But again, the expectation of a sum is the sum of the expectation. So I copied 1 over n, sum of the expectation. And now here you have something to say. Guys, which is the expectation of xi? Since the xi, I told you, are identically distributed to the population, you see, each xi has expectation mu. So the expectation of xi is mu. Then you have 1 over n times the sum from I equal to 1 to n of mu. What does this mean? This means that you have to sum mu to itself n times. What's going on here? Wait. Ah, okay. Thank you. Thank you, Mustafa. Thank you. Thank you. Okay, guys. So we have just shown that n times mu, simplify n, and you get mu. So you get almost the complete distribution of x bar. Since x bar is normal, I repeat, has an expectation, and we find out its expectation, its expected value. What does this mean, guys? That suppose that you select infinite samples. Select an infinite number of samples, guys, from your population. Compute for each observed sample small x bar. So in the first sample, you have a small x bar 1, in the second sample, another number, small x bar 2, etc., etc. Then do the average. What you get? The average of all the sample averages is mu. So this means that the expected value assumed by the random variable x bar is mu. This is the average value that x bar assume if you consider hypothetically an infinite number of samples, all the possible samples you can select from your population. If you suppose you select all the possible samples you can select from your population, compute for each sample selected small x bar, do the average of the small x bar computed in all your samples, so sum them and divide by the number of samples you select, of the samples, and what you get is mu. So this is the expected value of the random variable mu, of the random variable sample mean. So the expectation of x bar is equal to mu. So we got a very interesting result. We got that the expectation of the sample mean is equal to the unknown expectation of the population. You see, because the population is normal with mean mu and variance sigma square. So the expectation of the random variable x bar is equal to mu, which is generally unknown, guys, so we do not know it. We need to find the variance. The variance of x bar, so substitute into the variance is okay, first into x bar, put its definition. Okay. Again, 1 over n is a multiplicative constant, can be taken outside of the variance, but if you take it outside of the variance, you have to raise it to the power 2, property of the variance. So 1 over n squared times the variance of the sum of the xi. Remember, the variance of a sum in general is not simply equal to the sum of the variances, but you have to add also the double product between the covariances. I mean, the double product of the covariance between all the pairs of random variable. However, guys, what kind of random variable are the xi? The capital Xi are the element of a random sample. By definition, they are independent. So since the xi are independent, we know that for sure all the covariances are equal to 0. And therefore, due to independence, you see the reversed capital T. So due to independence, we know that the variance of the sum in this case is simply equal to the sum of the variances. But now, which is the variance of xi, capital Xi? Again, the xi are the elements of a random sample, so they have the same distribution of x. So the variance of the xi is equal to the variance of x, but the variance of x is sigma squared. So variance of xi for I equal to 1 to n is always equal to sigma squared. So I substituted here sigma squared. Now, we have the sum of sigma squared to itself n times. So sigma squared plus sigma squared plus sigma squared n times is n sigma squared. Simplify the n with the square, and what you get? Sigma squared over n. So we got this very important result. We find out what? We have just found the distribution of the random variable sample mean when the population X follows a normal distribution. So we have just shown by performing all the steps that if the population follows a normal distribution with mean mu and variance sigma square, now the random variable capital X bar, which is called sample mean, okay, follows a normal distribution too, with the same expectation of x, mu, and variance, which is given by the variance of x divided the dimension of the sample. So this is a very fundamental result. But I told you in this lecture, we will find other very important results. And look what read with me what I wrote below. Since the sample mean follows a normal distribution with mean mu and variance sigma squared divided by n, pay attention, by increasing the dimension of the sample, you are able to reduce what? The variance of the random variable sample mean. Bigger the dimension of the sample you are going to select, smaller the variance of x bar. In particular, if n is super huge, that is, let n to tends to plus infinite, what you get, you studied mathematics with me, guys, sigma square a number divided something that tends to plus infinite tends to 0. So what does this mean? This means that the variance, which is a measure of the variability, guys, tends to 0. So what does it mean? This means that x bars tends to be a constant. Remember, the variance of a constant is 0. So as the n tends to plus infinity, that is, bigger the dimension, smaller the variance of x bar. And in particular, if n tends to plus infinity, pay attention, this tends to 0. And so what will happen in this case? X bar tends to assume the value mu with probability 1. In other words, as n tends to plus infinity, x bar converts to a degenerate random variable, which is a constant equal to mu. And this is very intuitive, guys, because you know that this is a measure of the variability. If the variability tends to 0, which is in particular, guys, this is a measure of the variability of the values assumed by x bar around the mean. But if the variability around the mean tends to 0, this means that x bar will assume the value equal to mu. But guys, reason with me, what does practically mean that n tends to plus infinite? This means that your sample tends to be your population. So if n becomes bigger and bigger, as the dimension of the sample becomes bigger and bigger, then your samples tend to become more and more similar to the population. When n becomes really infinite, you have that your population and your sample are exactly the same. So if you compute the sample mean by considering all the population, obviously, guys, you studying your sample is the population, compute the sample mean using the complete population, obviously you get the mu of the population. Okay, now I want to show, we studied also a very important variable in the last lecture, which is the standard normal random variable. And I explained, if you have a normal and you subtract to a normal random variable its expectation, and you divide then everything by the standard deviation, what you get is a standard normal random variable. That is a normal random variable with expectation 0 and variance 1. So do it. I told you x bar, which is the expectation of x bar? Mu. So x bar minus mu, which is the variance of x bar? Sigma square over n. So which is the standard deviation? Is the square root of the variance. So divide x minus mu by the standard deviation of x bar. Okay, so sigma square can be taken outside of the root because, okay, sigma square is a square, so sigma over square root of n. You can keep it in this way, or better, this is the way in which you find this result. You can transform this ratio, this is the numerator, and this is the denominator, into a product. So into the product between x bar minus mu and the reciprocal of this one, which is square root of n over sigma. So this formula has been obtained by simply standardizing the sample mean. So by definition, this is a standard definition. I mean, we proved it even. It's a standard normal random variable because x bar was a normal. If you standardize a normal, you get always a normal random variable with expectation 0 and variance 1. So this is our standard normal random variable. So these are the two results that I wanted to show at the beginning, because I told you that we want to find the distribution of some random variables which are called sample statistics. And in particular, I showed the first case very simple, in which the function of a random sample was the function x bar, which was the sum of the capital Xi divided by the dimension of the sample. This is the case. Now, in a moment, we are going to study this case. Then we want to show this one and the case D. But before, I think I did a graph to explain the meaning of increasing the dimension of the sample. So I want to show, guys, what I told you here graphically. The intuition. What does occur when n increases to the distribution of x bar? Let me see, guys. I did it poorly. Suppose that, okay, I did it very poorly. Suppose that this is a distribution of, is a normal. Okay, I wanted to plot a distribution which is symmetric around the mean mu. Okay, I did it very poorly. Okay, very poorly. But this is, for example, the density. Here you if we want to report x here and f of x on the vertical axis, and this one, the one I'm touching now, the distribution with the lower peak, can be seen, for example, at the distribution of x. X, guys, is normal with mean mu and variance sigma square. So this can be seen as a distribution of x, but also can be seen as a distribution of who? Of x bar when n is equal to 1, because if n is equal to 1, that is, you consider a sample of dimension 1, you have that the sample mean is normal with mean mu and variance sigma square over 1. So you see that the distribution of x bar is perfectly equal to the distribution of x if n is 1. Suppose then you select you want to select a sample of dimension 10, which is the distribution of x bar 10, will be normal with mean mu and variance equal to the variance of the population divided by 10. Obviously, the variance in this case of x bar 10 is smaller than the variance of x bar 1, which is the variance also of the population. And so I plotted this one as an example, intuitive example. You see that I plotted this distribution, which has obviously a higher peak around mu, because it has also a smaller standard deviation. because remember, okay, I did really poorly. Here, this is the standard deviation, the distance between, remember, the inflection point and the center of the distribution. This is sigma of your of x1. Instead, the standard deviation, which is sigma over square root of 10, in this case, is simply the distance between the inflection point, where is the inflection point? About here, and the center. Remember, we did it the first lecture when I explained the meaning. So you have smaller, so what I'm saying is that the second distribution has a smaller dispersion around mu compared to the first one. Now suppose you select another sample of dimension 500 and the distribution of x bar 500, sorry, 50, not 500, sorry, 50, will be what? Normal with mean mu and variance sigma square over 50. And again, which is the standard deviation? Is the distance between the inflection point, okay, of this probability distribution and the expectation. So I think the inflection point you see is until here is convex, after here is concave, so it's about here. So this horizontal distance, which is very small, is the standard deviation of the sample mean when the dimension of the sample is 50. You see, as the dimension of this of your sample increase, you have a distribution with a higher peak around mu, which means a higher probability to assume value around mu. And in particular, if you let these two tends to plus infinite, what you get? You have that the variance tends to 0, that is, our function will assume the value mu exactly with probability equal to 1. So with probability equal to 1. Probability equal to 1. That is, x bar of infinite, x bar infinite here means that the dimension is infinite, is what? A degenerate random variable which will assume for sure the value mu with probability 1. That being said, we go to the second case, and after having finished it, we will do the break. Okay, but we think we need 20 minutes. Now, not case B, we want to show another very important sampling distribution, which is the distribution of this random variable. But in order to explain the distribution of this random variable, which I still have to explain, obviously, because I still have to say what is capital S hat square, I need to introduce another continuous random variable. Remember, for the moment, we saw one continuous random variable, which was the standard, the normal random variable, or if you want also, the standard normal, but okay, it's still normal. Okay, so one random variable we saw continuous. We want to see now another absolutely continuous random variable, which is called the chi-square random variable with n degrees of freedom. So in particular, guys, we denote a chi-square random variable with n degrees of freedom in the following way, with this capital letter, with this bar. So this, sometimes you can put also here, someone put also here another small line, but okay, I prefer to use this. This means the notation used to denote a chi-square random variable with n degrees of freedom. In particular, a chi-square random variable with n degrees of freedom is defined as follows. Is the sum from I equal to 1 to n degrees of freedom, the sum from I equal to 1 to n of what? Capital zeta I square, where zeta I is a standard, where the zeta i's, because you have n zeta I, are standard normal random variables, and these standard normal random variables are independent. So read with me. I wrote where capital zeta I, for I that goes from 1 to n, are IID. This means independent and identically, I wrote it here, distributed random variables. In particular, the zeta I are independent and identical distributed standard normal random variable. What does this mean in symbols, using mathematical notation? This means that Zeta I is independent with respect to zeta j. For I different from j, what does this mean? Zeta 1 independent from zeta 2, zeta 2 independent from zeta 3, zeta 1 independent from zeta 3. So when this index and this index are different, then you have independent random variables. So here you have zeta 1 plus zeta 1 square plus zeta 2 square plus zeta 3 square plus etc. zeta n square. Here you have that all these different n random variables are all independent, one with respect to the other. Okay, and this independent identically distributed means that all the zeta I have the same distribution, and in particular the distribution of zeta I is normal, standard normal. So the zeta I are all standard normal random variables, that is, they are normal random variables with expectation 0 and variance 1, and they are all independent. Now, by definition, guys, since the chi-square is with n degrees of freedom is the sum of n random variable, each one raised to the power 2, obviously a chi-square can always assume values bigger or equal to 0. It assumes the value 0 if and only if all the zeta I assumes at the same time the value 0. Otherwise, the value is strictly greater than 0. So for this reason, R plus here, I added it probably when I explained last year, means that the possible value that a chi-square can assume are value on the positive semi-axis of the positive, I mean, if you look at the horizontal axis, only on the positive part of the only on the positive part of the x-axis, this variable is defined. So this variable is defined only on the positive part of the x-axis and also at 0, because I told you that it can assume also, in theory, the value 0. And okay, so what you have to remember, which is the meaning of a chi-square random variable. A chi-square random variable with n degrees of freedom is the sum of the squares of n independent standard normal random variable. Stop. This is simply the definition. Here I reported only to make practice, only to make an exercise. You don't have to remember the next step, but it's useful to learn. Compute the expectation and the variance of a random variable x following, you see capital letter, following a chi-square distribution with n degrees of freedom. So what follows is only an exercise to play, okay? Only an exercise to play. Do it when you study, because it's always useful, very useful to learn, but you don't have to remember the result we got at point A and B. Okay, I did it only to make some practice together and for you at home. So expectation of x. X is a chi-square with n degrees of freedom. So is the expectation of what? Of the sum of the zeta I, capital zeta I square. Now, which is the expectation of a sum? You see, guys, I apply always the same property. So study, because it's not difficult. I apply always the same property. Is the sum of the expectation. The expectation of a sum is the sum of the expectation. Now, which is the expectation of zeta I square? Now, let me add something. In general, remember, guys, zeta I follows a normal 0, 1, all the zeta I, and we want to find the expectation of zeta I square. Remember that I use zeta I for since I want to be consistent with the notation used, which is the variance in general. Okay, I use zeta I, but this is true for all possible random variable. Definition, which is the equivalent way to compute the variance, is the expectation of what? Of the random variable square, expectation of zeta I square, minus, I do not have space so I go below, the expectation of zeta I, then raised to the power 2. Okay, so if you want to write, if you want to write, I told you that variance of zeta I is the expectation of what? Zeta I square minus the expectation of zeta I, then raised to the power 2. Okay. Guys, but remember, which is the variance of theta? Guys, oh, let me follow exactly what I did here. So look at this expression, guys. Look at this expression. What you need to find, you are interested in this expectation, okay? You see, we want to compute this expectation. So you can take this and put it in the first-hand side. So if you put it in the first-hand side, what you get? You get the variance of theta I plus the expectation of theta I squared, which is equal to what? The expectation of who? Theta I raised to the power 2. So the expectation of theta I raised to the power 2 is the variance of theta I plus, because you have to change sign if you put it in the first-hand side, the expectation of theta I squared. So substitute into expectation of theta I squared its expression, which is variance of theta I plus expectation of theta I squared, exactly as I did here. Okay, so I put it inside parentheses, okay, because this is the expectation of theta I squared, this one. Now, which is the variance of theta I, guys? Theta I is a standard normal random variable, so the variance is equal to 1. So I insert here 1, which is the expectation of theta I. Theta I are normal random variables, so the expectation of the generic theta I is 0. 0 square is 0. So you have to do the sum from I equal to 1 to n of 1. So this means that you have to do 1 plus 1 plus 1, etc., n times. And from that you get what? You get n. So we find out this interesting result, but not important. It's not important, guys, this result. For this reason, I tell you when something is not important to remember. If you remember everything is good, very super good, but this is detail which is not important to remember. You don't need also in application to remember that the expectation of a key square with n degrees of freedom is exactly equal to its number of degrees of freedom. But however, the computation is useful to make practice with the property of the expectation, with the definition of variance. Okay, now I asked you to compute the variance. The variance is more complicated. In fact, I provided here a result without proof. But we compute variance of x. Which is the variance of x? The variance of a key square with n degrees of freedom. So substitute into x the expression of a key square with n degrees of freedom. Again, guys, pay attention, please. You remember that in general, the variance of a sum is equal to the sum of the variances plus the double product of all the covariances between pairs of random variable involved. However, guys, think in this case, think at the definition. I told you that a key square with n degrees of freedom is the sum of the squares of n independent standard normal random variables. And independence. So guys, since the theta I, theta 1 and theta 2, for example, are independent, also their squares are independent. That is, theta 1 square is independent with respect to theta 2 square. Since theta 1 is independent, for example, with respect to theta 4, also theta 1 square is independent with respect to theta 4 square. Okay, so since the theta i's are independent, also the squares of the theta i's are independent. So see again, when I write this, always to remember you that I'm applying the property of independence. Thanks to independence, the variance of a sum is equal to the sum of the variances, because thanks to independence, the variables are linearly independent. But if they are linearly independent, you know that the covariances are all equal to 0. So thanks to independence, we have that the variance of a sum is the sum of the variances. But now, which is the variance of theta I squared? Apply the definition. Which is the variance of a random variable? Is the expectation of the random variable raised to the power 2. But which is the random variable now? Is theta I squared. So if you take it, the expectation of this one to the power 2, you have expectation of theta I to the power 4. Minus what you have, the expectation of the variable itself, which is the expectation of theta square I, but then you have to raise to the power 2 outside, okay? And here there is what I told you. I will not ask you to prove it because it's long. I need to use complicated things, characteristic function. But the expectation, guys, of a standard normal random variable taken to the power 2 is always equal to 3. So you are not required to okay, you see, I wrote it below. It can be shown that the expectation of a standard normal random variable taken to the power 4, expectation of theta to the power 4, is 3. Okay, is 3. So substitute 3 here, which is the expectation of theta I square. Guys, we got it previously. The expectation of theta I square, we got it here, was equal to 1. Guys, remember, the variance of theta I is equal to 1. This expectation is 0. So this term is equal to 1, but this term is exactly the expectation of theta to the power 2. So here insert 1, okay, to the power 2, which is 1. So 3 minus 1 is 2. Then you have the sum from n times, you have the sum of 2 to itself, n times 2 plus 2 plus 2, n times, gives as a result 2n. So the chi-square random variable has these interesting characteristics, that its shape depends only on one parameter, n. While a normal random variable is characterized completely by two parameters, mu and sigma square, a chi-square random variable is characterized only by one parameter, which is n, which is called number of degrees of freedom. In fact, you see that the variance is 2 times n. As I told you, what is important? Remember the property, the definition of a chi-square, which is very important. Then it's not fundamental that you remember that the expectation of a chi-square is equal to n. The variance of a chi-square with n degrees of freedom is 2 times n. It's not important that you remember that the expectation of theta to the power 4 is 3. If you want, okay, most thing you remember better is, but it's not so fundamental. Okay, I tell you when something is fundamental. The result about the sample mean we got previously and the standardized sample mean we got previously is fundamental. Here instead is fundamental to remember the definition of a chi-square, okay, and the result I'm going to show in a moment. In a moment, this one. The result I'm going to show related to this. But wait, we have almost finished this part, guys. Guys, here I will show that later, maybe not today, another day. I will show the tables. Okay, so don't be scared. We still have to show the tables. I told you the shape of a chi-square random variable depends on the number of degrees of freedom. Please, you don't have to remember also the graph I did here, but only the intuition. Guys, to review, a chi-square is a random variable. Its density, which is reported, is density, okay, f. Remember, since it is a density function, you know that the density function might always lie above the horizontal axis, so you can cancel everything below. Remember, by the property of the density is always greater or equal to 0. The density evaluated at a particular point is always greater or equal to 0. Then I also told you that the chi-square is the sum of the squares of n standard, normal, random variable, blah, 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 independent. Since the sum of the squares, I told you that the values that the chi-square can assume are always greater or equal than 0. In fact, remember that I was trying to tell you that this variable, the chi-square can assume value only on the positive part of the x-axis, which is this one. In particular, it can assume value 0. And as I told you, so you can cancel everything here. Now, you must not be able to plot it. I only to tell you which is the typical shape of a chi-square. As I told you, the shape of a chi-square distribution, I did not report the density, okay, because it involves gamma function, etc., and you don't really need to remember. It's good to remember the density of a normal random variable, but you don't need to know the formula of the density of a chi-square. However, I told you that the shape of a chi-square random variable depends only on the number of degrees of freedom. In particular, the pattern you have of the density of a chi-square with 1 degree of freedom is something like this. Here, something like this. The pattern of the density of a function of a chi-square with 2 degrees of freedom is something like this. wait, if you have 5 degrees of freedom, you have something like this. Bigger the number of degrees of freedom. Oh, let me try with my finger, but it's not important, guys, only to tell you. Bigger the number of degrees of freedom, you have something more and more like this. You tend to have, even if not symmetric, you tend to have something which seems symmetric. It's not symmetric because here goes from 0 to minus to plus infinity. So it's not really symmetric, but I mean, here is stop. I mean, here you cannot go beyond on the left of 0. However, what I want to tell you is that bigger the number of degrees of freedom, more symmetric tends to be the distribution. And remember that all the area below the density must be equal to 1. Now, only to get an intuition, guys, but I will show the table. In the table, you have only one picture, but typically you have something like this, a behavior like this, okay? Bigger the number of degrees of freedom, more on the right is more on the right the peak of the distribution, okay? But again, this was not important, okay? You have to remember the definition. What is important instead is what I'm going to tell you now, because it's a very useful result in statistics. So, as we did previously, to derive the distribution of the sample mean, I make again the same assumption. Assume that the population follows a normal distribution with expectation mu and variance sigma square. Now, define, guys, and we will talk about estimator later in the future, in a close future, tomorrow, call capital S square bar in this way, as the sum from I equal to 1 to n of what? Of the capital Xi minus capital X bar to the power 2 divided n minus 1. This is called, guys, unbiased sample variance. This is called unbiased sample variance. We saw already the sample variance given a sample, so that was a number in the first lecture. This is a random variable. Why? Because in the numerator you see I have the capital X1 minus capital X bar to the power 2 plus capital X2 minus capital X bar to the power 2, capital X3 minus capital X bar to the power 2, etc., etc. So you have in the numerator the sum of n terms, which are capital Xi minus capital X bar raised to the power 2, and these are random variables because the capital Xi are random variable, capital X bar is a random variable, divided n minus 1. If you had divide, guys, by n, if you divide only by n, imagine to divide only by n, you get another random variable, which is the sample variance. And guys, we studied without talking about random variables, but talking about the observed sample, we studied the sample variance. At the time, that was only an estimate, which was the sum of the small xi minus small x bar squared divided by n. If in the formula I gave you the first day, you substitute the capital letters in the numerator, you get the sample variance, but which is not an estimate, which is on the contrary, a random variable. In particular, if you substitute capital letter and in the numerator you divide by n minus 1 instead of dividing by n, what you get something that we will discuss in another tomorrow, which is called unbiased sample variance. So tomorrow it will be clear why I divided here by n minus 1. But for the moment, I want that you realize that s hat square is a function that depends on capital X1, capital X2, capital Xn, and also on capital X bar. So it's a function of a random sample. So it's a random variable. Okay, so look below. It can be shown that capital S bar hat, which is the unbiased sample variance, which is a random variable, multiplied by the following constant, which is n minus 1, where n, remember, is the dimension of the sample. So n minus 1 divided sigma square, okay, it is possible to show, I avoid to do the proof, this guys, because a little bit longer, not difficult, but a little bit longer. So it is possible to show that by assuming that the population is normal, then the distribution of this random variable is a chi-square with n-1 degrees of freedom. Okay, so this is also another very important result. And before doing the break, really last minute, look, s hat substitute into s hat square here its expression. Do it, guys. Substitute into s hat square its expression, which is this one. You see that if I substitute its expression here, I can simplify this n-1 with this n-1. So if I substitute this here, I simplify, and then I get what I reported here. The sum from I equal to 1 to n of the capital Xi minus capital X bar to the power 2 divided sigma square follows a chi-square with n-1 degrees of freedom. So it's very important that you remember this result in both ways, okay? In both ways, because very often in the course of econometrics, you will get result quantities similar to this one, and the professor will say, oh, this is a chi-square with, I don't know, n-k degrees of freedom, for example. Okay, and then you think about it and you say, oh, yes, I remember that I saw something similar, not maybe exactly equal, but something similar, so I can believe what you say, you can say to the professor. Okay, so guys, for a moment, now we do 1 minute and we do the break. I finished, okay, to talk. So guys, last minute, but I stopped to explain here. So this is the second important result. These results are fundamental. You will understand why they are fundamental tomorrow when we will do maybe, yes, the second part of tomorrow, maybe tomorrow afternoon, when we will do confidence interval and hypothesis testing, I think, but these are results that are very fundamental in inferential statistics. So it's very important to study these results, okay, because they are fundamental in inferential statistics. So as I told you now, guys, now we do, minute, okay, I forgot I have this, okay, and then we do the break. And during the break, guys, if you have questions, I'm still here. So really, last 30 seconds and I finished. Really, I forgot that I reported here these two properties, but I mean, two observations. Let x be a chi-square with n degrees of freedom, and let y be another random variable following a chi-square with m degrees of freedom. Assume that x and y are independent, okay? Then it follows that the sum x plus y is another random variable, obviously, which follows a chi-square with distribution with n and m degrees of freedom. Why? Intuition, guys. X is the sum of the squares of n independent random variables. Y is the sum of n independent normal random variables. Each one takes to the power 2, okay? So, but since y and x are independent, all the n standard normal random variable in the definition of this x are independent, but they are also independent with respect to the other m standard normal random variable considered in y. Also, the squares of the n standard normal random variable inside this chi-square and the m square standard normal random variable here are independent. So if you put them together, you have, if you sum them, you have the sum of n plus m standard normal random variable independent, each one taken to the power 2. So by definition, it follows that this is a chi-square with n plus m degrees of freedom. Stupid observation or stupid interesting? Which is the distribution of a standard normal random variable taken to the power 2. Guys, by definition of a chi-square, take theta square. What is theta square? Obviously, by definition, is a chi-square with 1 degrees of freedom, because it's the sum of what? Of a unique random standard normal random variable. So is a chi-square, I mean, is the sum, sum, it's not even a sum, it's directly chi-square, I mean, remember, a chi-square with n degrees of freedom, is the sum of the squares of n independent standard normal random variable. If you consider a random variable which is defined as only as a theta square, you have only the square of one standard normal random variable, and therefore you have a t-square with 1 degrees of freedom. Okay, guys, now 18 minutes of break, so we will continue at 10 minutes to 11. Okay, so so guys, go to rest. Some student wrote me, ask me now. I answered to ask me during the break or at the end of the lecture if you want, or even at the beginning. If it tomorrow, I be here 10 minutes earlier if you have question for me, and also before the lecture you can have I can answer the question. Go guys, go guys. If you have question, however, stay. People who wants to ask me question, they can ask me. Okay, now or later.
Good morning. I sent you an email this morning.
Okay. Yes.
Italian. And I have a lot of questions. The first one, it was about an exercise you published on your website.
Yes.
The simulation of an exam, and I'm referring to the first exercise of the set E.
Let me see. Oh, non ce l'ho qui. Dove l'ho caricato? Ah, forse posso scaricare. No, forse ce l'ho qua. Wait. No, maybe I have it here. No, yes, I have it here. I should. Let me see. No. Wait a moment. Crash course quantitative method. Which was repeated A, B, C, E. Okay.
Yeah.
Number?
The first one.
Ah, the first one. Yes.
Yeah, and first one exercise.
Yes.
Okay.
Yes. Which is your problem?
My problem is that you gave us a formula.
Yes.
And I don't know how to apply the formula if we have x, y, and j, because in the formula you gave us we only have x1 and x2. Because
but it's then we did the application at the end. Maybe you need to finish to review, but in the application we had at the end we had n random variable. It's the same, no problem. It's the linear. This is still a linear combination. This is normal. This is normal. You can have all the variables you want. Important things is that all the variables must be normal. So it's this one. S is a linear combination of x, y, and j. So it's a linear combination of normal distributed random variable with coefficient h, k, and minus m. We have also an additive constant. So this is still normal. Okay, this is still normal. If you look at the exercise we did at the end, we did two exercises at the end in which we had x1, x2, x3 until xn. But this really is the last exercise we did together. But this was really an exercise we did at the end after the explanation. But to show that the important things is that you can have 10 normal, 100. It's not the important thing is that all these variables must be normal. If all the variables are normal, and maybe you can even have an additive constant, the constant makes no problems, then you have the variable defined in this way is normal. From the expectation, I think you had no problems. I don't know, but if you have questions, no, you can ask me. You can ask me, okay? Even now, if you have a question, or maybe since you understood that it's normal, you want first to try to compute the expectation by yourself and the variance by yourself, then ask me, or otherwise we can talk now as you prefer.
Okay, thanks.
Well.
Also, I have another question. It's about the exercise 5 from the same set of exercises.
Okay. Yes. In this case, yes.
Yes. I don't know how to calculate.
No, I need to show the table. AE.
Yeah, that's
fine. I still to show. I still have to show you how to use the table, so it's not important. In fact, I told you do only the exercise 1, but okay, in this case, in principle, you can do. Let me see. Okay. Yeah. Yes. In principle, you can do everything. Only this one I still have to show you but I need to show it with the table. But first, I wanted to finish this part. And yes, because I will show the table of the chi-square that I just introduced the chi-square, but I still have to show how to work with the table. You have another file. Among the theory, you have a file which is called table. You need to use the table, but I will show how to use them. Okay.
So I have another doubt.
Yes.
Is that you did an exercise during the last class, and
Yes.
you asked us to calculate the covariance of
Yes.
two. I can't remember
For two samples. Yes. Yes.
Yeah, and I was. I don't know if we have a different amount of
No, you have the same amount because you are measuring two characteristics of the same type of individual, of the same individuals. Okay, so you must have both data. So, as I mentioned, must be the same. Okay, because you are measuring two characteristics of the same individual to study the covariance. You cannot mix them. So no, you must have the same dimension. Okay.
And my last question is about
Yes.
It's about a formula you gave us.
Yes.
The properties of the variance. And
Yes.
I don't know to demonstrate it. It's the I sent you a photograph in the email.
You wrote the solution.
Yeah.
Your
You
solution.
gave us the solution, the formula, but I was asking.
No. I mean, you sent me your solution. I mean, you tried.
No, yeah, I tried, but
No, because if you sent me the solution, I can tell you where you did the mistake if you did it. Because if you try, send me if you scan it, or otherwise we read it together. Let me see. Let me open the file.
But was not able to do that.
Okay, let me open the file. Let me open my file, which was random variables. So let me take it. Let me take it. No, ok, questo è qua. Allora, so I can open directly here. Random variables. Variance. No, l'ho già passata forse. Oh no, it's before. Yeah. Wait a moment. Welcome. Sì, qui saranno qui. Ah, qui, here. No, for the variance, no, the covariance you told me.
I'm sorry, the variance.
It's for the variance?
Yeah, I sent you a photograph if you.
No, it's not because I think you sent this one because I saw that you wrote me and then
Yeah. So I'm sorry. It was about the covariance. Yeah. The penultima formula.
Questa qua l'hai fatta, quella sopra? Did you do this one?
Quella sopra sì. Non riesco a dimostrare quella sopra.
Ok. La posso scrivere. Adesso un po' di spazio. Qui no, troppo piccolo, aspetta. Allora. Because you should take the expectation. I need the space to write. Well, let me see. I need to install first another thing. So wait, or maybe let me. Well, wait. We're doing this way. I write it and then I upload it. Okay.
Okay.
Yes, because I need time to make the computation and space especially. So I will do it after the lecture if you want. I mean in the afternoon or after the lecture, depending if students have questions for me, I will do it later. Otherwise, I solve it on a sheet of paper and I will then put it on the chat so the student can find it if they need. Okay.
Thank you.
No, because I do not have the space, because if I had already installed here open board, but to solve a technical problem I had with this PC, and I don't know. Sometimes I need, te lo dico in italiano, delle volte questo PC che è nuovo, avete visto che mi è capitato un paio di volte, credo, a perdere la connessione, e ogni volta devo disinstallare tutto per poterlo riportare allo stato originale, e quando lo riporto allo stato originale per un po' funziona bene poi, e quindi tutte le cose che ho installato vengono automaticamente disinstallate, quindi dovrei reinstallarle. Non ho reinstallato la lavagna, perché magari con la lavagna avrei potuto scriverla. Ok, quindi scriverò la soluzione in un foglio. I will write the solution in a sheet of paper, and I will take a picture, and then I will upload it here. Ok?
Ringrazio.
Bene, bene, prego. Vai a riposarti 8 minuti almeno.
Professore,
Sì, dimmi. Sì, dimmi.
scusi,
Sì?
excuse me in English.
Puoi parlare anche in Italiano. You can talk also in Italian, since we are
Ok,
simply
perfetto.
here outside the lecture. Yes.
Perfetto. Volevo chiederle una cosa anch'io. Del test C, l'esercizio 4, il punto B. Quindi
Del
test C,
4, aspetta.
test C.
Adesso devo riprendere, devo chiudere che non è qui, è di qua. Crash course, quantitative method, vado qui. Allora, C.
Esatto, il test C. Ok, l'esercizio 4.
Ok, yes.
Ok,
Sì, dimmi,
allora
dimmi.
io ho provato a fare il punto A e, cioè, nel senso, non so se l'ho fatto bene, però ho calcolato l'expectation di Y e la
Sì,
varianza di Y. Dopo aver
sì.
fatto questo, però, non riuscivo a capire come calcolare il punto B, quindi la correlazione di
Allora,
XY.
scrivi, adesso te lo dico. Te lo dico. Poi questo qui probabilmente qualcuno magari me lo chiederà anche all'ultima lezione, ma intanto tu che l'hai fatto fai bene a chiedere. Allora, la correlazione che cosa è uguale? The correlation is given by the... fammi vedere quindi, aspetta. Suppose that x and... Ok.
Perché io ho pensato...
Ok. No, adesso l'ho letto, adesso ho capito. Remember, allora, la correlazione è uguale alla covarianza, ti ricordi, divisi il prodotto delle deviazioni standard. Questo te lo ricordi?
Esatto, sì. Sì. Però ho pensato di non
Allora,
avere i dati per poterlo calcolare così.
no, in realtà ce l'hai, perché prima, allora, qual è la deviazione standard di x? Ce l'hai, che è la radice di 4, giusto? 2.
La
Ce l'hai
direzione
quella.
standard è certo, lo dice, certo.
La deviazione standard di y la puoi calcolare, la puoi ottenere, perché allora qui funziona così. La
Forse
correlazione ti
perché io ho
verrà...
calcolato prima. Scusi,
No,
scusi.
no, allora, no, è perché qui bisogna fare un po' di calcoli prima, adesso, no, allora, sicuramente dovrebbe venire correlazione -1, però adesso spiega, però non volevo che lo faceste direttamente così. Allora, ti spiego perché deve venire -1 la correlazione, ma non è questo il modo, questo diciamo il modo più smart, ma io mi aspettavo che faceste i calcoli. Il modo più smart è questo. Guarda com'è definita Y. Com'è definita Y?
Sì,
È
come
una
se fosse una
trasformazione
trasformazione lineare.
lineare, quindi è perfettamente una trasformazione lineare perfetta di x, in particolare il coefficiente di x è -2, è negativo, quindi vuol dire che c'è proprio, se uno volesse rappresentare la loro relazione, è una relazione lineare discendente, quindi è proprio perfetta, quindi verrà -1. Comunque, quello che invece dovreste fare, a parte questo che era il metodo più rapido, è questo. Allora, prima trova la distribuzione di y, infatti mi dici cosa hai trovato? Hai detto che è normale, immagino, perché è una trasformazione lineare di
Sì,
una...
perché è una lineare, esatto.
Ok,
E poi ho calcolato l'expectation che mi
quanto
viene
ti viene? Che
-1.
dovrebbe essere, expectation di y dovrebbe essere -2 per 1, -2 più 1 fa -1, giusto?
Esatto. E la varianza mi viene 16.
La varianza, fammi vedere, la varianza di y è 4, per la varianza di x 16, ok, 16, allora hai fatto bene. Quindi la deviazione standard è 4 di
4.
y.
Sì.
Allora abbiamo la
Quindi
deviazione standard di y che è 4, la deviazione standard di x che è 2,
2, quindi il denominatore è 8.
sì, ci manca la covarianza. Allora, scrivi pure
Mhm.
cov xy
Sì.
uguale cov, apri la parentesi di nuovo, al posto di
Mhm.
x metti ancora x, virgola,
Ok.
al posto di y metti la sua definizione che è -2x più
Più
1.
1. Perfetto.
abbiamo visto nelle proprietà dell'altra volta che se hai la covarianza tra due variabili, la costante additiva non ha nessun
testo, sì.
effetto. Quindi sarebbe, facciamo un altro passaggio, è covarianza di x, virgola, meno 2x. Ti torna?
Ok, sì, sì, sì.
Allora, qual è il... Ricordati che abbiamo visto la formula, che era una tra quelle di dimostrare a casa, che covarianza di ax più ax e by puoi portare fuori a e b. Quali sono
A
a
e
e
B.
b? Sono i coefficienti
1 e
x.
meno 2.
Ecco, quindi è meno 2 per covarianza di x con x.
Varianza di x con x.
Ah, non ve l'ho
Ok.
detto questo. La
Oddio, no,
covarianza di...
forse sì, mi
Oh,
sfugge.
non l'ho scritto. No, ma mi sembra di non averlo detto, perché di solito ricordo tutto quel che dico. Mi sembra di non aver detto che la covarianza, forse è scritto, ma non ve l'ho detto, forse non è neanche scritto, che la covarianza di una variabile con se stessa, se vai a applicare la definizione, è la varianza. Quindi ti viene meno 2 per varianza di x, perché covarianza x con x è la varianza di x.
E la varianza di x è 2. Quindi è
È
meno 2 per 2.
4, è 4 se ci guardi, la
Sì,
varianza.
scusi, 4, 4.
Quindi ti viene meno 8. Abbiamo detto che il denominatore era 8, infatti vedi meno 8 diviso 8 fa meno 1.
Meno 1. Perfetto, ok.
Poi qua vi devo
Perfetto.
far vedere ancora le tavole per chi non le sa usare ancora, ma per fare il punto C vi devo far vedere ancora come si calcola la probabilità, quindi quello ve lo devo fare ancora
Quindi
vedere. Il B
il
non...
punto C non l'ave...
No, non ve l'ho spiegato ancora il C.
Ah,
Il
perché
punto A e
pensavo
B
di
vi
farlo
faccio
con
sapere...
l'integrale.
Sì, sì, ma in realtà usiamo le tavole, quindi va benissimo, non
Ok,
devo spiegare le tavole. Ecco, io vi ho detto solo con l'integrale che vi ho detto non dovete farlo, ma ci sono le
ok.
tavole, ve le devo
Infatti.
spiegare ancora. Prima devo finire
Perfetto.
prima. Ok, tutti il random sampling, ok. Ok, quindi fate così, anche se volete a volte, anche 10 minuti prima della lezione, io di solito ci sono 10 minuti prima, salvo un problema col PC e cerco di risolverlo, di solito ci sono anche 10 minuti prima, così se per sbaglio hai più domande puoi distribuirle come vuoi, ok?
Perfetto, perfetto. Grazie mille allora.
Niente, niente, grazie a te. Allora, chiudo questo. Un minuto e ripartiamo, eh? Ai, ai, ai. Aiuto. Allora, un minuto e iniziamo. Okay, guys, now we continue. Now I want to show you the distribution of another random variable or sample statistic, which is this one, capital X bar minus mu over S hat, where S hat is the unbiased sample standard deviation, which is the square root of S hat square, times square root of n. However, I need, in order to show you which is the distribution of these sample statistics, I need to introduce another absolutely continuous random variable, which is the student's t random variable or student's t distribution. So we saw the normal, and today we saw also the chi-square and the student's t. Guys, don't be scared, because we have tables for this variable, and I will explain a lot of things I still have to explain. So at the end, we will have everything, but for the moment, I need to start from a point. So student's t distribution. A student's t distribution with n degrees of freedom, denoted as Tn, is defined as follows. Tn is a ratio, I don't write because everything is below, between a theta, where this theta is a capital theta, is a standard normal random variable, and the square root of what? A chi-square with n degrees of freedom divided by its number of degrees of freedom, where theta and the chi-square random variable are independent. So you see that is the ratio of two random variables, theta and what? The square root of a chi-square divided its number of degrees of freedom, where theta and this chi-square are independent. I wrote it here, guys. Everything with NDF means degrees of freedom. Okay. In particular, guys, only to talk, maybe it can be useful sometimes to remember, but that the expectation of a student's t distribution with n degrees of freedom is equal to 0. The variance of a student's t distribution with n degrees of freedom, it is possible to show that depends only on the number of degrees of freedom, and is in particular n over n minus 2. Observe that the variance is well defined only if n is greater than 2, because if n is equal to 2, you have 2 over 0, which is not a real number. If n is smaller than 2, for example 1 minus 2 is minus 1, you have n, which is positive, divided minus, you have a negative variance. A negative variance does not make any sense, okay, because it's an average of squares. So the variance is well defined if and only if n is greater than 2. In particular, guys, I didn't write it, but I'll show. A student's t distribution is a distribution which is symmetric around 0, is symmetric around the mean. In particular, since you studied with me mathematics, guys, as n increases, you see the variance depends only on n. So suppose that n becomes bigger and bigger. So the number of degrees of freedom is higher and higher. So which is the variance? As n tends to infinite, what you have? Infinite over infinite. We studied it. And you have in particular the ratio of two infinite of the same order. So the result is the ratio of the coefficient. We did it, okay, so I don't explain mathematics again, is 1 over 1. So 1 over 1 is 1. So as n tends to plus infinite, the variance of a student's t distribution tends to 1. Guys, have you ever seen a distribution with expectation equal to 0, variance 1, which is symmetric around the mean? Yes, you saw it. It's a standard normal. So as n tends to plus infinite, the student's t distribution tends to the standard normal random variable. A student's t distribution is, in general, is a distribution with the bigger variability compared to the standard normal. Why? Because, I repeat, they are both symmetric distribution around 0. They have both expectation 0. They are both symmetric around 0. So this means that they have the median, and what I want to tell you is that the median, also for students t distribution, the median, the mode, and the expectation are the same, because they are symmetric both around the mean, which is 0. Look at the variance. You have n over n minus 2. So in general, the numerator is bigger than the denominator, you see. See, it's bigger. So this ratio is bigger than 1. Okay, but as n increases, this ratio tends to decrease from above, tends to 1 plus if you want to be precise. Okay, so what I'm saying is that the variability around 0 of a student's t is bigger than the variability around 0 of a student's t, of a zeta random variable. So the zeta is a more precise random variable compared to the student's t because it has a smaller dispersion around the mean. However, as n increase, the dispersion of the student's t around 0 tends to decrease. And in particular, as n becomes bigger and bigger, the student's t tends to become a standard normal. We say that asymptotically, the student's t distribution as n tends to plus infinity, I wrote it here, tends to the zeta. This is what I wrote here. To get an intuition, guys, only an intuition, I plotted some very poor graph. So remember, look at the peak. Okay, here I did really poorly with my hands. I did really poorly, I know. So, for example, this was my goal. Look at this distribution, the one with the lowest peak. This is, for example, a student's t distribution with 10 degrees of freedom. So it's symmetric around, should be perfectly symmetric around the mean, which is here. So you see, is symmetric. The mean, the median, and the mode are the same, 0. And look what occurs. Suppose, for example, that the next one, this one is the density graph, the density function of the student's t with 20 degrees of freedom. As the number of degrees of freedom increase, we have that the peak around the mean becomes higher, okay, becomes higher, and the variability around the mean decreases. That is, you have a bigger mass of probability around the mean. In particular, as a last example, suppose that TD student n tends to infinity is very huge. Essentially, the student's t tends to the standard normal, which is this one. Okay, well, standard deviation is equal to 1. So the standard deviation of a student's t, the distance between the inflection point and the center of the distribution for a student's t, in general, is bigger than 1. But as n increase, then the variance and therefore the standard deviation decrease and tends to 1. When n is huge enough, you can, instead of working with the student's t distribution, you can work directly by using the zeta distribution. But this when n becomes huge. So what you have to remember for the moment, which is the definition of a student's t distribution with n degrees of freedom. And you have to remember that is a symmetric distribution around the mean. And as n tends to plus infinity, the student's t distribution tends to the standard normal. This is what you have to remember about the student's t. That being said, we are going to see the third very important result in statistics. And the third result you have to remember is the following. If x is normal, so if the population follows a normal distribution with expectation mu and variance sigma square, you see that in all the three cases we studied until now, I made this initial assumption. Then it is possible to show that x bar, capital X bar, minus mu over s hat times square root of n follows a student's t distribution with n minus 1 degrees of freedom. In particular, now, I want to show this result as I did for the first one. In particular, because the proof is useful to remember, I mean, to learn. Okay, you don't have to show me the proof in the exam. You have to remember the result, because this result will be used in confidence interval and in hypothesis testing, so it's fundamental as the previous three. Well, I want to prove this result. In particular, guys, we know that if x is normal with mean mu and variance sigma square, we know that the sample mean, first result we have shown this morning, we know that the sample mean follows a normal distribution with expectation mu and variance sigma square over n, which is equivalent to say, remember the always first result, that the standardized sample mean follows a normal 0, 1. This is, we proved both results this morning. Then I provided another result without proof later, before the break. I told you that another important result under this assumption was that n-1 over sigma square times the unbiased sample variance, which is s hat square, okay, follows a chi-square with n-1 degrees of freedom. Guys, are you able to build using result in point A and result in point B a student's T distribution? Yes, you should be. Because guys, there is something more to say. And I wrote it here. It is possible to show, guys, that x bar, which is the sample mean, and s hat square, or simply s hat, are independent. So it is possible to show that x bar and s hat square are independent. But since x hat, this one, sorry, x bar and s hat are independent, then also x bar minus mu over sigma times square root of n, which is only a transformation of a normal random variable, is independent with respect to what? To s hat square times this constant. So these and these are independent. So this standard normal random variable is independent with respect to this one. Remember that I told you that a student's T distribution with n degrees of freedom is a ratio between a standard normal divided the square root of a chi-square with n degrees of freedom divided its number of degrees of freedom. So guys, here you have a standard normal random variable. Here you have a chi-square distributed random variable with n minus 1 degrees of freedom. You have also that these and these are independent. Well, so you have all the instrument to build a student's T distribution or a student's T random variable with n minus 1 degrees of freedom. In fact, look, remember the student's T, as I told you, you have the ratio in the numerator between a standard normal. We have it because I told you that this is standard normal. Divided the square root of a chi-square. Well, we have yet a chi-square. Look, square root. This is a chi-square. This result at point A and point B, guys. The two fundamental results. Divided by its number of degrees of freedom. And also, I told you, this theta and this chi-square are independent. So this is exactly the definition of a student's T. But a student's T with how many degrees of freedom? This was a chi-square with n minus 1 degrees of freedom. Divided n minus 1. So this is a student's T with n minus 1 degrees of freedom by definition. So guys, you see, you can simplify this n minus 1 with this n minus 1. Then, if you want, you can take both this and this outside of the square root. So you have, copy the numerator, you see as it is, this one is the numerator. And below you have s hat divided sigma. If you don't see, you can simplify this with this. If you don't see it, do another step. Multiply the numerator by what? By the reciprocal of this one, okay, times s hat, times sigma over s hat, and you can simplify sigma and sigma. And so what you get is simply x minus mu over s hat times square root of n, okay, but we have shown, I told you that this was a student's T, so we have shown that by simplifying that this strange quantity, this strange random variable follows a student's T distribution with n minus 1 degrees of freedom. If you go back, this is what exactly we wanted to prove. This is a very important result. We have shown, so for up to this moment, we got 3 results. If x is normal with mean mu and variance sigma square, this random variable or sample statistics follows a standard normal. This random variable or sample statistics follows a chi-square distribution with n minus 1 degrees of freedom, that they are independent. Furthermore, these sample statistics or random variable follows a student's T distribution with n minus 1 degrees of freedom. Can you please, only to think with me, compare these two results? Are they similar? What does this represent, guys? This is the sample mean standardized using the true standard deviation of sigma of the sample mean, because which is the true standard deviation of sigma bar of x bar is sigma over square root of n. So if you standardize the sample mean using its true standard deviation, what you get is a standard normal. Look above. What is it? Compare. This is the sample mean standardized using not the true standard deviation of x bar, which is sigma over n over square root of n, but by using s hat over square root of n. But which is the meaning of s hat, guys? I told you that s hat, it can be shown tomorrow, it will be shown tomorrow that s hat square is the unbiased sample variance, is the estimator of sigma. It estimates, it's used to estimate sigma square. So s hat is used to estimate sigma square. S hat is a random variable. Sigma square is a constant unknown of the population. So if you standardize x bar by making use not of the true standard deviation, sigma over square root of n, but by using an estimator, s hat square root of n over square root of n, then this modifies the distribution of the standardized mean, which is no longer a standard normal, but which is now a student's d with n-1 degrees of freedom. But as I told you guys, intuition, this distribution is less precise than this one because they are both symmetric around 0, but the variance of this one is bigger. Okay? Intuition. As n increases, I told you, the student's t tends to the normal, but as n increases, the dimension of the sample increases. So if n tends to infinity, if you estimate the variance of the population by using s hat square, what you get is essentially you get sigma square. This is why, so I understand, so when n becomes infinite, essentially you have that this tends to the normal 0, 1. Why? Because as n becomes to infinite, s hat tends to sigma, because you are computing the standard deviation essentially of your population. So these are three very important results, guys. And even if you don't remember the proof, which is, I repeat, when you study it, but then if you forget, it's not important. But when you study, you have to follow, because you see application of all the concepts we studied together. Because to get the proof, you see, we applied result at point A and B, and result at point A and B holds because we made this assumption. So this is the third important result in statistics, and this is fundamental result. Now, the last result, this is called, and I want to show you the ratio, which is the distribution of these sample statistics or random variable. I will explain what it is, but first, in order to explain this one, which I still have to introduce, I need to first talk about a fourth continuous random variable, which is the so-called f of Fisher, or Fisher's f, capital F distribution. So as I did for the chi-square, as I did for the student's t, I need to provide the definition of an f of Fisher and some property, but really few properties. An f of Fisher random variable with n of nodes and m of mother degrees of freedom, denoted as capital F n m. So this means an f of Fisher random variable or an f of Fisher distribution with n and m degrees of freedom is defined as follows. Is a ratio between what? Don't write because I wrote everything below. A chi-square with n degrees of freedom divided its number of degrees of freedom, and another chi-square with m degrees of freedom divided by m degrees of freedom. So the number degrees of freedom here refers to the number of degrees of freedom of the chi-square you have in the numerator. The number of degrees of freedom here, it refers to the number of degrees of freedom of the chi-square in the denominator. I have also to tell you something else. this chi-square and this chi-square must be independent. So is the ratio between a chi-square divided its number of degrees of freedom and another chi-square divided by its number of degrees of freedom when the two chi-squares are independent. So this n refers to the chi-square in the numerator and this m to the number of degrees of freedom of the chi-square in the denominator. I wrote everything below. Okay, you see I wrote it here. Okay. By definition, guys, by definition, this is always greater or equal than 0. This must be strictly positive, okay, because it's in denominator. So is the ratio of a quantity which is always greater or equal than 0 divided a positive quantity. Obviously, the values that in f of Fisher with n and m degrees of freedom can assume are value greater or equal than to 0. Okay, so by definition, is a non-negative random variable like the chi-square. Guys, we do not care about the mean. We do not care at all about the variance. It is possible to show, okay, that both the variance and the mean depends on n and m. And in general, the shape of the distribution depends only on n and m. So this distribution is characterized completely by two parameters, n and m. Remember, guys, the normal distribution in general, the general normal, is characterized completely by two parameters, mu and sigma square. A chi-square is characterized by only one parameter, n, the number of degrees of freedom. A student's t is characterized completely by only one parameter, n, the number of degrees of freedom. F of Fisher is characterized completely by two parameters, n and m, respectively the degree of freedom of the numerator and the degrees of freedom of the denominator. Okay, with this one I stop with this f of Fisher, but I wanted to show a very important result in application in statistics and econometrics. In particular, guys, remember that to get result A, result B, and result C, we assume that X was normal, the population was normal with mean mu and variance sigma square. In this case, guys, we have two different populations. We have a random variable X, and we assume that this random variable X follows a normal distribution with mean mu X and variance sigma square X. I called X because in this case I had two variables. So, and then you have another population or random variable Y that follows again also a normal distribution with mean mu X and variance sigma square Y. And we assume also that X and Y are independent. So the two populations are independent. Okay. Suppose that you want suppose nothing. Suppose you want to select two samples. You want to select a sample of dimension, say, n from small n, from the population X, and you select another sample, suppose in general that the dimension of this sample is m. So not necessarily equal to n, okay? They could be also equal, but I want to be general. So you know that this is what? A random sample from this population. This is a random sample that you want to select from this population. So a random sample, remember, is a vector of n independent. This one is a vector of n independent and identically distributed random variable to the population. This is the same, but for the second sample, okay? So all these variable follows have the same distribution of X. All these random variables have the same distribution of Y. Okay, now go on. Then what do you know, guys? This was from B, from result B, from the fundamental result number B. We know what? We know that S hat square X, which is S hat square X, guys, is the unbiased sample variance. The unbiased sample variance relative to the random sample X. Okay, so since we have two samples, I denoted it with the X and not simply with S hat square. We know that the sample unbiased sample variance times what? N minus 1, because the dimension of this sample is n, so times n minus 1 over the variance of the population follows a chi-square under with n minus 1 degrees of freedom, because under the assumption that X is normal, we know this result. This result B we got today. We use it also to prove result C. So again, since Y is normal, and this is a random sample, we have a similar result concerning Y. Concerning Y, in particular, we have S hat Y square times what? Which is the dimension of this second sample? M. So multiply it by M minus 1 divided by the variance of the population, and by applying again property B, we have result B. We know that the distribution of these sample statistics or random variable is a chi-square with M minus 1 degrees of freedom. Guys, additionally, since these two samples, X and Y, are independent, so also this estimator, the unbiased sample variance of X and the unbiased sample variance of Y are independent. Okay? They are independent, okay? These and these are independent. Fate vedere se l'ho scritto sotto. Oh, I didn't write it, so add here. I'm explaining, but I forgot to write it. So what I'm saying is that since I add this one, because if you study otherwise, say why the professor didn't mention it. So let me see. Since X independent from Y, Y, then S hat square is independent with respect to S hat square Y. Then, remember, here you have this times a constant, this times a constant, so also this is independent with respect to this one, thank you to this one, thank you to this condition. So we can say that this chi-square n minus 1 is independent with the chi-square with n minus 1 degrees of freedom. Okay, guys? Okay, guys. Now there is a very fundamental result. No, fundamental. Guys, I'm asking you, are you able to build an f of Fisher? Yes, because an f of Fisher is a chi-square, is a ratio between two chi-square independent random variables, each one divided by its number of degrees of freedom. So do it. This is a chi-square. This is independent with respect to this one. So we have two independent chi-square. In the numerator, for example, I put this one, for example, which is this one, divided its number of degrees of freedom. Everything divided by what? This chi-square divided its number of degrees of freedom. You see that you can simplify this with this with this, and you get this one. You can either stop here, or alternatively, you see, you can transform this ratio into a product by multiplying this one by the reciprocal of this one, which is reported here. If you want, you can put under the same ratio what? The two unbiased sample variances. So you have this over this one, and times what? The variance of the population Y and the variance of the population X. But by definition, guys, what is this? This is a chi-square with n minus 1 degrees of freedom divided its number of degrees of freedom, divided by an independent chi-square with m minus 1 degrees of freedom divided its number of degrees of freedom. So by definition, this is a chi-square with n minus 1 and m minus 1 degrees of freedom. So we find out this result. Observation, guys, before going below. Obviously, you can get another chi-square. For example, if you exchange this numerator, this one, with this one, what you get? You get an f of Fisher with m of mother minus 1 degrees of freedom and n minus 1 degrees of freedom. So what I'm saying, guys, if you exchange the numerator with the denominator, you get s square y over s square x times sigma square x over sigma square y, and in this case you would get an f of Fisher with m minus 1 and n minus 1 degrees of freedom. So this result, as we will see, will be very important in inferential statistics. that is in both building confidence interval for the ratio of two variances, as we will see, and to perform hypothesis testing. Before going on, I made an observation, guys. I made an observation here. The square of a student's t random variable with n degrees of freedom is an f of Fisher with 1 and n degrees of freedom. In particular, guys, how can you define an f of Fisher with 1 and n degrees of freedom? Do it with me, guys. By definition, an f of Fisher with 1 degrees of freedom in the numerator means that in the numerator you must have a chi square with 1 degrees of freedom divided by 1, which is the number of degrees of freedom. But as I explained below when we studied the chi square, a standard normal random variable taken to the power 2 is a chi square with 1 degrees of freedom. So a standard normal to the power 2 is a chi square divided by is a chi square with 1 degrees of freedom, so divide by 1. So this is a chi square with 1 degrees of freedom divided by 1. Then divide by what? You must divide by a chi square with n degrees of freedom. So chi square divided n degrees of freedom. But guys, how can you rewrite it? It's simply if you look here. Okay, this, okay. Guys, which is the square root of this one? Is theta over 1 divided the square root of a chi square divided by, with n degrees of freedom divided by its number of degrees of freedom. Okay, assuming that this theta is independent with respect to the chi square, also the square of theta is independent with respect to the chi square. Okay, so what is the chi square? So what does this prove? Look, this, if you define a random variable which is the square of an f of Fisher with 1 and n degrees of freedom, what you get? Guys, what it is? The ratio theta divided by 1 is like to say theta. Theta, a standard normal, divided the square root of a chi square divided its number of degrees of freedom, where theta and the chi square are independent. By definition, at point C, this is a student's t distribution with n degrees of freedom. So the square root of an f of Fisher with 1 and n degrees of freedom is a student's t. So if you, on the contrary, consider the square, if you want, if you, on the contrary, raise it to the power 2, you get a student's t. You see, with a student's t raised to the power 2, you get this. Okay, so this is a student's t distribution with n degrees of freedom raised to the power 2. But by construction, this is also an f of Fisher with 1 and n degrees of freedom. Okay, guys. So for the moment, I've shown you 4 fundamental results. All the results we got have been obtained by assuming that the population, think to case A, B, and C, were normal. In case D, the last one we studied, we had 2 populations, and we assumed that both populations were normal. So in those cases, we find out the exact distribution of 4 sample statistics or 4 random variables, and we got the exact distribution because we did everything, and this was really by following the properties. So we did everything correctly. So these are exact distribution. But what does happen if you cannot make assumption about the distribution of the population? What does occur if you cannot say that the population is normal? Well, there is another important theorem, fundamental theorem in probability, which is called central limit theorem. This is an important theorem related to probability theory, in probability theory. And I will tell you this theorem because it plays a very fundamental role. So, central limit theorem. Given a sequence of random variable, capital X1, capital X2, capital Xn, which are independent and identically distributed with expectation mu and variance equal to sigma square, build the sample mean capital X bar n. Okay, we study capital X bar. Here I simply put the n, which is related to the dimension of the sample, which is defined, as you know, the sum of the capital Xi divided by n. Okay, So we have essentially, guys, I'm saying, given a sequence of independent and identical distributed random variables. Guys, have you ever seen something similar? You can say, given a random sample in other terms, because a random sample, guys, is a sequence or a vector of independent and identical distributed random variables. So given a random sample, alternatively, you can say, given a sequence of n independent and identical distributed random variables with mean mu and variance sigma square, or alternatively, given a random sample, capital X1, capital X2, capital Xn, then build the sample mean, which is a random variable, define then the standardized sample mean. You remember how can you standardize? Yes, you have to subtract to the sample mean its expectation. But which is the expectation of the sample mean, guys? Is mu. Divide by its standard deviation. Which is the standard deviation of the sample mean? Result A, guys, is sigma over square root of n. So rewrite it and call this random variable as zeta n. Okay? Well, the theorem establishes the following. Then, as n tends to plus infinity, that is, as the dimension of the sample increases, then the distribution of the random variable zeta n, which is the standardized mean, tends to the standard normal. So what is different here with respect to what I explained in case A? In case A, guys, I told you that x bar minus mu over sigma times square root of n follows a normal 0, 1, but we proved it. But we proved it by assuming that the population X was normal. On the contrary, in the central limit theorem, you see, I simply told you, given a random sample, but I made no assumption about the distribution of X. I simply told you, given a random sample, that is given a sequence of n independent and identical distributed random variables, then if you have this sample, as the dimension of the sample becomes bigger and bigger, then the standardized sample means tends asymptotically to the standard normal random variable. So it's different. While in case A, I assume that X was normal, and I find out that X bar minus mu over sigma times square root of n followed exactly a standard normal distribution. In this case, zeta n follows this distribution only asymptotically. So in this case, you cannot say that zeta n follows a normal 0, 1, but then bigger n, better the approximation you get for the distribution of zeta n if you approximate it by using the standard normal. The approximation becomes better and better as the dimension of the sample becomes bigger and bigger. This is called central limit theorem. It's very fundamental because it allows you to approximate the distribution of zeta n by using a standard normal distribution, even if you do not know, you know nothing about the shape of the distribution of the population. Then I think, then guys, I made this table to simplify everything. And this table is fundamental, I think already for tomorrow afternoon, or maybe even morning. Because these guys here in this table, I reported all the results you need in the exam. Not all, you have other results, but about this topic. About this topic, guys, I reported 4 fundamental results multiplied by 2. In particular, I built the table in this way. Fundamental result, I reported both exact distribution, you have the first column, and asymptotic distribution. In the asymptotic distribution, I provided the results was proof is based on the central limit theorem. On the first column, instead, I reported result based on the assumption of normality. As you can see, look with me, I reported this result, which was the result we find out at point A, the standardized mean. We know that if X is normal, the standardized mean follows exactly a standard normal random variable. Instead, look here. Here, the only assumption I make is n is huge. If n is huge, we can say that the standardized mean follows asymptotically a normal 0, 1. So if you use this approximation when n is small, well, this approximation is really poor and you are committing mistake. However, if n is big enough, the dimension of the sample is big enough, you can use this approximation. Obviously, this approximation becomes only exact when n becomes infinite, but when you work with the sample, obviously the dimension of the sample is finite, is not infinite. So here we say, guys, this A means that the distribution of the standardized mean is asymptotically normal 0, 1. That is, bigger the dimension of the sample, better the approximation of the true distribution of this quantity, which is unknown, obtained by approximating it by using the standard normal. Then remember, I called it C. In reality, this is case B. Guys, wait a moment. In the derivation we did is case C, this one, and this is case B. However, in building the table, I built this as case B because, as you will see tomorrow, when you work, you need to establish if you are either in this case or in this case, because this formula, guys, I reported here, here, and here, as we will see tomorrow, are useful to build confidence interval or to perform hypothesis testing concerning the expectation unknown of the population, which is mu. But okay, you don't have to understand now, okay? I'm simply saying that tomorrow, depending on the case, we will need to start from this one, or from this one, or from this one. For this reason, I reported one under the other here. Then result C, which is in our derivation is B, is this one. Oh, guys, let me finish. In the case X is normal, we find out this result. In this case, you cannot make any assumption about the distribution of the population, but n is huge, you can use the asymptotic result. The asymptotic result is the following, that establish, guys, that as n tends to plus infinite, the standardized mean through the sample unbiased standard deviation asymptotically converges to the standard normal. So this is the exact distribution, this is instead the asymptotic distribution. And the approximation becomes better and better as the dimension of the sample increases. Then here you have, under the assumption of normality of the population, you have that this follows exactly a chi-square with n minus 1 degrees of freedom. By using the central limit theorem above, it is possible to show that if you make no assumption about the distribution of x, or even if x is not normal, then asymptotically this sample statistics tends to the chi-square with n minus 1 degrees of freedom. Then last result, this is the last result we got, and this is an exact result under the assumption that x and y are both normal and they are independent. Okay. On the contrary, in the case in which you cannot make assumption about x and y, and you cannot assume, but however you still can assume that they are independent. I'm saying you cannot assume that is normal and this is also normal. You have that this quantity, if x and y are independent, has an asymptotic distribution, which is still an f of Fisher with n minus 1 and n minus 1 degrees of freedom. So this result, I repeat, I will never repeat enough, are fundamental. For the moment are simply result for you. And you say, why do we need them? Who cares now? Don't care now. The important thing is that you understood when I derived. I mean, you need to study. But to do this, obviously, you need to review and study. This is important for the moment. You will understand why we need this result. You will understand it when we will build confidence interval and when we will perform hypothesis testing. Okay, so now I want to show only one thing now. I stopped to explain theory, but we still work for other 10 minutes at least. No, 10 minutes. And I want to start to show the tables. At least let me show, we will see if I'm able to show only one table. So I close this, but remember, these results are very fundamental. I built it also, I built it also formula for confidence interval, etc., but you will see. Okay, so stop here. Tomorrow we will continue, no, stop here, I mean with the presentation. Tomorrow we will continue with yes, tomorrow we start inference. Yes, inference. Maybe we finish. I don't know. No, finish. No, I don't think. Well, maybe we'll do something. Well, maybe finish the theory, because then we have also a lecture on the exercises. First, I need to finish inference at least. Okay, but however, that being said, with the theory stop, but I open the table. So I opened now the file table. Guys, sorry, this is in Italian, but I tell it for English, for foreign students, guys. This means table 1. This is cumulative distribution. This means cumulative distribution function of the standard normal random variable. So table 1, cumulative distribution function of the standard normal random variable. You know, to review, guys, that the standard normal random variable has expectation 0 and standard deviation equal to 1. So guys, this is the vertical axis is here, okay, is here on 0, okay, on 0 you have the vertical axis. On the vertical axis you have the density which is, remember, capital zeta is the random variable, and small zeta, this is small zeta, is one of the possible values that zeta can assume. Zeta, capital zeta, can assume values from minus infinite to plus infinite. So all the possible value that zeta, capital zeta, can assume are all the real numbers, that is, all the horizontal axis, the x-axis. And here, this letter, guys, denoted is phi, for us is what we call f of small zeta. F of small zeta means the density evaluated at zeta. So here you have, for example, the value small zeta. This vertical distance is phi zeta, or f of zeta, that is the density evaluated at zeta. Remember that all the area above the horizontal axis and below every density function is always equal to 1. So the complete area is equal to 1. Here, guys, the function continues. I mean, here you have an horizontal asymptote, as I explained. So it's very, 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 very close to the horizontal axis, but we will never touch the horizontal axis. Then here is 0 is the mean, the median, and also the mode. I explain now how to read the table, how to use the table. Here you see, you can compose value of zeta by looking first at the column and then at this row. For example, guys, reason with me. Here you have, read this number is 0.0, and here you have 0. So this number essentially, guys, is combine this with this, you have 0.00. So essentially 0. Okay. So, and which is the meaning of this result? You look here. Look here, guys. Look at this result. 0.5. I explain it. So zeta 0.0 essentially here. This means the probability that capital zeta, a standard normal, will assume a value smaller or equal than 0.00, small zeta, where small zeta is 0. So small zeta is this one now, is 0, which is the probability that, I do it poorly, that a standard normal random variable will assume a value smaller than 0, guys. You must know by yourself. I told you the standard normal is symmetric around the mean. So this area on the left is equal to the area on the right. But which is the total area, guys? It's 1. So 1 over 2, okay, is 1 over 2 is 0.5. Exactly. So in other terms, 0.5 is the probability that a standard normal random variable, capital zeta, will assume a value smaller than small zeta, when small zeta in particular is 0.00. Look at another one. Which is the meaning of this number? This number represents always the green area, the probability on the right of zeta, or small zeta. Which is small zeta in this case? Is 0.0, see the 0, 0, 1, which is the probability that a standard normal random variable will assume a value smaller than 0.01 is a little bit bigger than 50%. You see 0.5040. Okay, now which is, let me cancel. So looking at the table, you understand how the table are, we explain only this one, okay, today, only this one. only this. Then you have other table, okay, but you have also the student's D, the chi-square, the f of Fisher in the table I provided here. But today we explained already too many things, and we almost finished, and I want only to finish this one. Okay, tomorrow we will continue with confidence interval, and at the end, when we have some time, we will look also at the tables. Okay, let me see, which is, guys, so you see, this, so inside, with the exception of the first row and the first column, all the numbers inside corresponds to this green area where the value theta is obtained by crossing first the column and then the row. For example, I'm asking, which is the probability that a standard normal random variable will assume a value smaller than 0.45? 0.45. I repeat, which is the probability that a standard normal random variable, I write here. So 0.45 is theta, okay? Suppose it's here, so this is theta. So we want to find, suppose this is 0.45, we want to find this green area. How can you do it? Well, for the first decimal, you have to look here. So you are here, 0.4. You need the 5. Okay, so go. Oh, here you see 0.4, 0. The 4 goes here, 5. So go below, go below, go below. So the probability that a standard normal random variable will assume a value smaller or equal to 0.45 is 67,36%. Okay, look. This is the typical, I mean, you see, you can use this table to compute probabilities. Okay, but you can also apply the reverse problem. Last 2 minutes, guys, then I let you go. But we will do it again when we will do confidence. I told you guys, I need to explain inferential statistics, but then we will do exercises on inferential statistics, and then we will work a lot with tables, okay? For the moment, I simply introduce this table. Suppose, guys, I ask you, find the percentile, guys, because this one, on the horizon, the values of the theta are also called the percentile. Remember the percentiles, the deciles, the quantiles, or quantiles. The theta are also quantiles. We typically use percentiles and quantiles as synonymous. To be precise, should say quantiles, because percentiles, you have 99 percentile. Okay, but okay, suppose you want to find the percentile. I'm asking you, find the percentiles such that, or the percentile 99, or in other terms, the percentile such that the probability that capital theta will assume a value smaller than small theta is 99%. That is, find the value of theta, in other terms, such that, and then we stop, guys, because we will work it after having done confidence intervals and hypothesis testing. Find the percentile such that this green area is 99%. So, guys, you know that, and we finish, guys. Let me finish this example. You see, you know that the green area are this number corresponds to green area. So what you have to do? You have to find the first 0.99 inside the table. The first one, because it's the smallest one. Yeah, here. Well, you don't have exactly the 0.99, but you see, here you are very, very, very close, because you have 0.9898, here 0.9901. You can even do an average or other interpolation, but who cares? Or maybe if you want, stop here for today, you can take this one, which is closer, you see, this is closer to 0.99, okay? You can, for example, take, therefore, look this one, 2.3, and then you have to go, so you have 2.3, so then you have to go above this column, so you have 0, 1, 2, should be 33. 2.33. So, in fact, there is a probability of 99% that a capital theta will assume a value smaller than small theta, when small theta is 2.33. To be precise, this probability is 99.01%. Alternatively, you can do an average between 2.33 and the other one, which was associated to this one, which is 2.32. Because if you go below, and really I finish, guys, stop, you can go. I'm simply telling you that you can do the average if you want between 2.32, which corresponds to this value of probability, and this one, but directly, guys, why? You are already precise enough if you consider directly 2.33. But okay, don't be scared about the use of the table, because we will work again a lot with the tables, but for the moment I want to give you only an introduction. So guys, go away unless you have question for me, and probably tomorrow I will show one of the chi-square probably, and I don't know. But here you have the other table, I will explain them, and obviously we will work also with them when we'll do exercises. But for the moment, I have some minutes, so I introduced it. Okay, so first I will introduce the table, but then we will work a lot with them, so you have time to refresh, to review again everything. So don't be scared. Only the first introduction if you've never seen them. Okay, guys, do you have questions? If you have questions, guys, on the exercises, on what we studied today, or what I gave you for home. And I told you that only for this time I solve I will upload later a proof of an exercise I gave you for home, but only this time. Okay, unless you have the girl who knows, I will upload it. But okay, if you have question, guys, you can stay to make me question. Otherwise, have a good lunch. See you. I think tomorrow. It's tomorrow for 6 hours, I think. However, if you have question, I stay here. If you have question, otherwise you can go and have a good lunch.
Okay, thank you. Bye.
Bye. If you have question, wait and say, Prof, I have question. Okay, bye.
Thank you. Bye.